Hello, welcome back, Physics 30. So we are going to get into the last lesson here, Chapter 15, Lesson 4. And we're going to get into the last kind of two models of the atom. All right, so Bohr's model of the atom here, it was looked like this, right? N1, N2 working its way out. Okay, but it had a few weaknesses. Number one, there's a lot of higher level elements it couldn't explain the spectrum of. Okay, it couldn't explain why. So we knew that it could only be at level 1 or level 2 or level 3, but it couldn't explain why. Why was level 1 here and not here, right? That kind of stuff. Okay, so that's kind of the idea. And it doesn't explain if you split into several lines using magnetic electric field. But the main one is that why? Why can we only be here? All right, so comes along De Broglie. De Broglie, you'll remember from the last chapter, okay, he's the one that said, well, electrons are actually waves, right? They're actually waves and particles, and that's important. So electrons up until this point were always considered just particles, all right? And what he says is he took the idea, okay, well, we got one wavelength, right, of a wave. He said, well, one wavelength of the wave is probably, if we were to wrap it around the nucleus, okay, that is equivalent to one orbit, right? And so if I have two wavelengths, I will have an orbit out here. And if I have three wavelengths, I'll have an orbit out here. If I have four wavelengths, I'll have an orbit out here, right? And so the first orbit is one wavelength, second orbit is two wavelengths, three wavelengths. And so what it shows is why. Okay, so Bohr's quantum condition, the condition for stationary states, is that the circumference of the circle or of the orbit has to be an integral, meaning an integer, right? So positive whole number. So it can be one wavelength or two wavelengths or three wavelengths, but it can't be 30.6 wavelengths. Okay, it has to be exactly a whole number, right? And so that's where we get this constructive interference, right? So this is a good example. So when I have perfectly exactly, right, peak to peak is a wavelength, right? So I have exactly five, 1, 2, 3, 4, 5. I have five wavelengths here, and they're perfectly overlapped, right? And what that means is that the electrons can exist there and be in constructive interference with each other. If I'm going to go trying to fit four wavelengths on there, it wouldn't work, right? Four wavelengths does not work because they're not the right lengths. And so this kind of shows that, well, okay, so every model before, right, had the electrons as a particle that orbits just like the sun or the moon orbits the earth, right? Or the earth orbits the sun, right? But now we're getting into that weird part of atomic physics and quantum physics where, well, these little things, even though they behave like particles, sometimes also behave like waves. But that's good because you can't explain this with a particle model. You can only explain this with a wave model. And so now what we've got is that wave-particle duality coming together to create Bohr's basically model, which is the same as um, uh, Bohr's model, and De Broglie's model. Okay, and so that's the idea is that De Broglie kind of brings the next level, all right, into that. Okay, you can show this if you watch this video. It's kind of a number that these waves kind of bend and flex and flow, right? They'll flex in and out these waves as they go because they have interference. And if you look at it, it looks very similar to minute 46 of this video if you want to click on it. Okay, you can actually click through these. Again, you won't be able to do it on your Chromebook. If you have a computer, it's really good to pull that up and use JavaScript and all that stuff. Okay. Yeah. So, okay. So that's kind of that's literally the last one I expect you to understand. Okay. Then you get into the Schrodinger. All right. So, um, the wave particle of matter means that it's impossible for us to know both position and momentum. All right, this kind of leads to the Schrodinger and Schrodinger's cat and kind of the uncertainty of things. All right, and this is extension. I'm not going to ask you questions or anything like that. All right. Um, so basically, what you get is what's called results in electron cloud. And so by us not knowing if an electron is a wave or a particle at that exact moment, and with us only knowing its position, so we can know exactly where it is, we can know it's here, but we can't know how fast it's going. Or we can know how fast it's going, but not its position, right? And so what we get this idea of an electron cloud, all right? And so what this looks like is basically you have your nucleus, right? Your nucleus is large enough that it doesn't regularly behave wave-like properties. And then we have the idea of electron cloud. Now I'm just going to use this kind of red. And electron cloud is kind of going to be a little bit, it's basically saying that electrons could be anywhere in here, right? Okay, so that's kind of a ground state, is the electrons are probably in this area somewhere, most likely, and then they're less likely to be out here, etc. If I excite those electrons, right? So this is when all the electrons are at N1, right? They're the first level. If I have them at N2, I excite the electrons to N2, then what happens is we get this cloud kind of moves out, right? So now the electrons are probably in this area. Now this cloud is not actual electrons. This cloud is just saying the probability of these electrons is higher where it's darker, right? So it's most likely going to be right at the center of this cloud, right? But it's because it's probably there, but it could be anywhere outside of it, right? And so there technically is a probability that the electron, when it's at N2, exists here, right? It could exist right here. That's where the electron could actually be. We can't predict it though. The most likely scenario is electrons there or kind of in this ring. So it's the most likely scenario is where it is. But it's kind of, since I said those rings vibrate in and out, then there's a probability that it's here. There's also a probability it's on Mars, technically, right? And so this is kind of where we get into some very, very, very interesting ideas. And we can't really say exactly where stuff is because it's a wave and it's a particle and it kind of leads back and forth. It's very confusing. All right, so this is the last one. This is Schrodinger's model. Okay, this is the most current model. It has no flaws that they've found yet, but as you guys can see, we have taken every model and we've developed and made it better, right? And so this is what research is kind of looking into right now, is like string theory and all that kind of stuff is leading into why does this happen and why can we not why can we not map this any farther? Why is it just probability? Why can't we know exact, right? And so it bothers physicists that we don't know. We know it's probably somewhere, not exactly where. So anywho, that's at end of chapter 15. One chapter to go, you guys. Yeah, let me know if you have any questions.